Hey everyone, thanks for tuning in to another episode of Fascinating Frontiers. I'm Patrick, coming to you from a drizzly Vancouver morning, and I'm genuinely excited to walk you through what the cosmos has been whispering about lately. There's something really special about these moments when separate threads of astronomy suddenly braid themselves together. Today, we've got stories that stretch from the quiet magnetic heart of dying stars all the way out to the far side of the moon and back again to our own backyard solar system. Let's dive in. We'll start with one of those beautiful aha moments that ties two completely different observing techniques into a single coherent picture. For a long time, astronomers have noticed that some white dwarfs, the dense Earth-sized remnants left behind after stars like our Sun exhaust their fuel, show surprisingly strong magnetic fields on their surfaces. At the same time, astroseismologists using missions like Kepler and TESS have been listening to subtle vibrations inside red giant stars and finding evidence of strong magnetism buried deep in their cores. Now, a new theoretical framework from the Institute of Science and Technology Austria pulls those two observations together. The team shows that the magnetic fields we see on white dwarfs aren't freshly minted during the star's death throes. Instead, they're fossil fields, magnetic structures generated very early in the star's life, probably during its main sequence phase when convection and rotation could amplify a modest seed field. These fields then ride out the chaotic red giant phase, staying locked inside the contracting core while the outer layers balloon outward and eventually get shed. What's left is a white dwarf whose carbon-oxygen heart still carries those ancient field lines frozen into its crystallized structure. I find this story quietly profound. It means that something planted billions of years earlier, maybe even while the star was still happily fusing hydrogen on the main sequence, can survive the most violent structural upheaval a star ever experiences and still be detectable 10 billion years later. For our own Sun, this gives us a much clearer forecast of what its magnetic future holds once it becomes a white dwarf roughly 5 to 6 billion years from now. The work beautifully demonstrates the power of combining astroseismology, essentially turning starquakes into a diagnostic tool, with high-resolution spectral data that reveals Zeeman splitting in white dwarf atmospheres. And here's the part that really gets me. If you could somehow shrink the Sun down to the size of a basketball, those core magnetic field lines would be strong enough to levitate a fridge magnet from the far side of a football field. Yet those same lines, stretched, twisted, and compressed over cosmic time, can persist through a star's death and reappear on its shrunken corpse. Some white dwarfs show surface fields reaching 100 million Gauss. That's millions of times stronger than Earth's field, while others seem to have lost their magnetism entirely. The big open question now is what initial conditions in a newborn star decide whether its magnetism becomes a fossil that outlives the star itself. It's the kind of puzzle that makes you want to keep watching. While some magnetic fields play the long game inside dying stars, other cosmic giants are locked in a far more urgent and violent dance. Astronomers have just confirmed the first close pair of supermassive black holes caught in a tight orbit inside a single distant galaxy. These two monsters whirl around each other once every 121 days, close enough that current theoretical models predict the pair will merge within the next century. That's an eye blink on cosmic timescales. The discovery offers a rare, direct look at the final stages of what happens after two galaxies collide and their central black holes eventually find one another. Galaxy mergers are one of the main ways galaxies grow and evolve over cosmic time, and watching the black holes themselves spiral inward gives us real observational data on one of the most energetic events the universe can cook up. The gravitational physics at play here is extraordinary. Space-time itself gets churned like butter as these objects draw closer, and when they finally merge, they'll release a colossal burst of gravitational waves that future detectors like LISA should be able to pick up. It's thrilling to have an actual system caught in the act, rather than just theoretical predictions. This observation is going to help refine our models of how black hole pairs form, how they shed angular momentum, and what their merger rates really are across the universe. It's a reminder that the most dramatic chapters in a galaxy's life story often happen on timescales we can actually watch if we look in the right place at the right wavelength. From black holes spiraling toward dramatic endings, let's swing over to a giant planet in our own solar system whose invisible shield turns out to be surprisingly lopsided. A fresh reanalysis of data from NASA's Cassini mission has revealed that Saturn's magnetosphere, that vast bubble of magnetic protection carved out of the solar wind, is not centered on the planet's core the way we once assumed. Instead, the magnetic bubble sits noticeably offset from the center of the planet. This offset suggests that the dynamo processes generating Saturn's magnetic field follow different rules than the ones that power Earth's field. On our planet, the magnetic field is generated by convective motions of molten iron in the outer core, and the field is pretty well aligned with the spin axis. But giant gaseous worlds like Saturn and Jupiter appear to run on their own dynamo playbook, probably involving metallic hydrogen layers under crushing pressure. The finding is forcing theorists to go back to the drawing board and rethink how magnetic fields are generated and maintained inside these massive, rapidly rotating fluid bodies. It's one more reminder that the rules we learn from our own pale blue dot don't always scale up neatly. I'm genuinely curious and a little impatient to see what new computer models emerge from this discovery. Every time we think we understand planetary magnetism, the gas giants hand us another curveball. Speaking of invisible forces that shape entire cosmic landscapes, a new idea about dark matter might help tidy up several long-standing puzzles at once. A team led by researchers at the University of California, Riverside, is proposing that dark matter isn't smoothly distributed but instead forms dense clumps, each weighing roughly 1 million solar masses. What makes this model particularly compelling is that the same single idea seems to simultaneously explain several different anomalies. Oddities seen in gravitational lens images, the behavior of stellar streams that have been tugged by unseen mass, and the puzzling distribution of tiny satellite galaxies around the Milky Way and Andromeda. It offers an elegant, unified framework that works across vastly different cosmic scales, from the tiny dwarf galaxies on one end to the bending of light by massive galaxy clusters on the other. That kind of theoretical elegance always catches my attention. Dark matter has been surprising us for decades, and this self-interacting clump scenario feels like real, tangible progress rather than just adding another free parameter. It doesn't solve everything, of course. Dark matter remains one of the biggest mysteries in physics, but it's exciting when a single hypothesis starts pulling multiple loose threads together. Dark matter may be hiding in dense clumps far beyond our reach, but right here in our own solar system, we're still finding brand new things about planets we thought we knew pretty well. Using the Gemini South Telescope's powerful immersion-grating infrared spectrograph, astronomers have measured the ratio of magnesium to silicon in the atmosphere of the ultra-hot Jupiter WASP 189b. What they found is striking. The planet's atmospheric composition closely mirrors that of its parent star. This result gives us one of the cleanest, most direct looks yet at how stellar and planetary chemistry are linked during the messy process of planet formation. It lends strong support to the idea that many planets essentially inherit their raw materials straight from the same collapsing molecular cloud that formed their host star, rather than having their chemistry heavily reprocessed along the way. For an ultra-hot Jupiter, a world so close to its star that its dayside temperature exceeds 3,000 degrees Celsius, having this kind of pristine compositional match is especially telling. The extreme heat should be driving all sorts of interesting chemical reactions and atmospheric circulation, yet the stellar fingerprint remains clear. These kinds of precise abundance measurements are adding crucial pieces to the larger puzzle of how different types of worlds assemble around different types of stars. Every new atmospheric study like this brings us a step closer to understanding whether our own solar system's architecture is typical or whether we're the odd ones out. While we're learning how planets inherit chemistry from their stars, another quiet but powerful experiment has been listening for something entirely different from the far side of the moon. China's Chang'e 4 lander, sitting patiently in the South Pole Aitken Basin, conducted the first dedicated search for extraterrestrial intelligence signals from a site that is naturally shielded from Earth's radio chatter. Because the moon always keeps the same face toward us, its far side is one of the most radio-quiet places in the inner solar system. No television broadcasts, no radar, no satellite chatter leaking over the horizon. The experiment didn't detect any artificial signals during its observation window, but that was never really the main point. What matters is that we're already putting that pristine radio environment to practical scientific use. The mere fact that we can deploy sensitive antennas on the lunar far side opens up observing possibilities we simply cannot access from Earth's noisy surface. I love that this kind of experiment is happening now, not in some distant future. It's a gentle reminder that our nearest celestial neighbor still has a lot to offer as an observing platform, especially for low-frequency radio astronomy, and yes, the patient search for other minds among the stars. From one lunar surface mission to another, NASA has just laid out its most detailed vision yet for staying on the moon for good. A new agency document maps out plans for sustained human presence, including 73 additional landings beyond the current Artemis flights already on the books. What really caught people's eyes wasn't just the ambition, but the clean, almost elegant graphic design that made the roadmap feel concrete and real. This isn't about flags and footprints anymore. It's about shifting from occasional visits to continuous operations, with habitats, power systems, resource utilization, and science outposts working together over decades. Building that kind of permanent presence is going to take steady political commitment, a lot of international cooperation, and even more commercial partnership. The fact that the agency is thinking on this scale feels genuinely exciting for the future of exploration. We've talked a lot over the years about going back to the moon. This document suggests we might finally be serious about staying, and that permanent presence will rely heavily on the creativity and speed of small companies, which is why yesterday's signing of new legislation feels timely. On April 13th, President Donald Trump signed the Small Business Innovation and Economic Security Act. The bill extends the Small Business Innovation, Research, and Small Business Technology Transfer programs through September 30th, 2031. It includes stronger screening for applicants while still preserving those vital early-stage funding pathways that have helped so many space startups get their first ideas off the ground, sometimes literally. Programs like these have been behind everything from lightweight materials to propulsion breakthroughs that larger contractors later scaled up. I'm glad to see them supported for the next several years. Steady, predictable funding for small innovators is one of those quiet enablers that often makes the flashy missions possible. Speaking of launches and hardware, SpaceX is about to hit a significant milestone with its Starlink constellation. The Starlink 10-24 mission will loft another 29 satellites into low Earth orbit. Liftoff is scheduled for 5:33 a.m. Eastern Daylight Time on a Falcon 9 from Cape Canaveral's Pad 40. When this flight climbs out, it will bring the company to its 1,000th Starlink launch of the year. The sheer pace of these deployments is remarkable. What started as an ambitious side project has become a machine that's rapidly expanding global connectivity from space, bringing high-speed internet to places that never had it before. It's a striking example of how fast the satellite industry is evolving, and how quickly we're wrapping the planet in a new kind of infrastructure. While we're sending thousands of satellites into Earth orbit, one large international team has been working hard to get a much more fundamental number right. A global collaboration has produced a more precise measurement of the Hubble constant, that crucial figure that tells us how fast the universe is expanding. The work cleverly combines complementary observational techniques, some anchored in the early universe, like the cosmic microwave background, and others based on the later universe, like supernovae and galaxy distances. The result helps narrow the long-standing tension between those two different ways of calculating cosmic expansion. Getting this number right matters because it touches everything from the age of the universe to its ultimate fate. I really appreciate the careful, patient work that goes into these cosmological measurements. They don't make headlines the way a black hole merger does, but they're the quiet scaffolding that holds our entire picture of the cosmos together. Keep an eye on how these refined Hubble constant values might influence the next generation of cosmology missions. They could end up telling us whether there's new physics lurking beyond our current models. Before we wrap up, I keep coming back to that white dwarf magnetism story. The idea that a magnetic field can be generated early, survive the red giant inferno, and then sit quietly inside a white dwarf for 10 billion years is oddly moving. It makes me wonder what it would feel like to stand on the surface of one of those tiny, ultra-dense stars, feeling ancient magnetism that's been waiting patiently since before Earth even existed. The universe is full of these long games, and every now and then we get smart enough to notice them. That covers today's tour of the cosmos. If one of these stories sparked your curiosity, share it with a fellow space enthusiast. These conversations are how we all keep learning. I'm Patrick in Vancouver. Clear skies, and I'll talk to you again tomorrow. 378. This podcast is curated by Patrick but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.
Drifting softly through the black. A million stars behind our back. The void hums low.